Yeah, so I'm going to, pointer. I'll be talking about high dimensional uncertainty quantification via multi-level methods. I'm a grad student at the University of Colorado in the Applied Math Department. I'm working with Christian Kettleson, also in the Applied Math Department, and my advisor, Alireza Dustan, in the Aerospace Department at the University of Colorado in Boulder. And our funding, and we were funded by the DOE PSAAP project. So an outline of my talk, I'm going to discuss the motivation of our research, then go into our numerical approach, discuss multi-level control variates for most of the talk, and that's kind of where our research is, and then the results and wrap it up. So for our motivation, our funding is from the PSAAP2 project. That's the Predictive Science Academic Alliance program, and this is led by Stanford University. And the aim of the project is to simulate particle-based solar cells, solar receivers. And within our subgroup of the project, we are looking at how the size of the particles affects the system. So this model will be looking at the specific domain. And when we get these particles from the manufacturer, they're not all the same size. Their diameter is given by normal distribution. So given that uncertainty, we'd like to quantify different aspects of the system. And it's a very high dimensional system. When I say high dimensional, I don't mean the domain, I'm talking about the stochastic input. And our particle diameters are going to be on the order of 100,000. So we're going to have, I should restate that, we're going to have on the order of 100,000 particles, and the uncertainty is going to be within their diameter. So another group is going to be working on the code for this, and that's not quite ready yet. So in the meantime, we're going to consider a preliminary problem. We're going to consider a thermally driven cavity flow problem. And so we're just going to be looking at the unit square domain, and we're going to be considering a couple stochastic boundary conditions. So our setup is this image, and we have this cold wall on the right and a hot wall on the left. And our cold temperature, our boundary condition, is going to be 100 degrees plus this 50-term KL expansion, where our eigenpairs are from the squared exponential covariance function. And our Z's are uniformly distributed between -1 and 1. Then on the left, we have our hot wall temperature, which is going to be given by this uniform distribution, and our viscosity will also be given by a uniform distribution. So our initial data, well, and our boundary conditions, our C is going to be our input, stochastic input, and it's a 52-dimensional problem. So our objective is to approximate the expected value of the average heat flux along the hot wall after the simulation. So Q is capital Q will be our heat flux, and this bold-faced little q is the heat flux along this whole wall. So when we're thinking about modeling on a certain mesh size, we're going to be having a vector that is going to have the heat flux evaluated at each grid point along the hot wall. And for our discretization, we're going to be using the two-dimensional incompressible Navier-Stokes using finite volume. So for a numerical approach, we have to consider the fact that we're in a fairly high dimensional system, and then down the road, we will be having even higher dimensions. So some methods we might consider, one of the first ones, which is fairly accurate, is expansion/collocation in polynomial spaces. So this would be stochastic Galerkin or stochastic collocation or even sparse grid collocation. This isn't quite what we would want because the cost grows quickly in the dimension D. Most of these, the cost will grow exponentially in the dimension. So as we get a larger and larger dimension D, the stochastic dimension, we're going to have a lot of issues finishing the simulations. So that brings us to the standard Monte Carlo method. What we're going to do is we're going to approximate the expected value of our heat flux, Q, by the discretization, the discretized solution, Q sub m. So m represents our grid. And we're going to estimate that with this sample estimator, Q hat. And that's going to, how we're going to get that is just draw n samples, run n simulations, get n quantities, and just take the average. So this has, So this, we can decompose the mean square error of this process into the sampling error. So that's the variance of our quantity divided by n, the number of samples that we draw, plus the discretization error. So there's positives and negatives to this. The negative is that our root mean square error converges in order 1 over square root of n. This is pretty slow, not ideal. The good news is it's independent of the dimension d. So we can consider ways to improve the error. The first thing we would want to do is refine the mesh. We have to do this regardless to decrease the discretization error. No one wants to solve on a coarse grid. And then the second two, we can choose either of them, or we can do both. We can increase the sample size n, so run a lot more simulations, or we can use a variance reduction technique so that we don't have to draw as many samples. And we're gonna go along the route of variance reduction technique. And this brings us into a well-known variance reduction technique for Monte Carlo methods, and that's the multi-level Monte Carlo. And basically what we're gonna do is, again, we're approximating the expected value of our heat flux with a discretized quantity, and now it's gonna be n sub capital L, where capital L denotes the level. Well, little l denotes the level, capital L is the finest grid. And we're gonna write this out as a telescoping sum, where we have the expected value of our coarse grid quantity plus the expectations of these correction terms. So these are the quantities on adjacent coarse and fine grids. And so all the MLs are gonna be nested grids. So from this image, we can see ML minus 1 is perhaps an 8 by 8 grid. From running a simulation on this mesh, we get this quantity, Q sub ML minus 1. And then again, we could run a simulation on our fine grid, which is a 16 by 16, and get Q sub M little sub L, and then take the expected value of that difference. So what we're gonna do now is change the notation a little bit. We're gonna change all the correction terms, the Q on the fine grid minus Q on the coarse grid, to Y's. Just for ease of notation, so we can think of our Y as a correction term. And our Y naught is just gonna be our quantity on the coarse grid. So what we're gonna do is we're gonna estimate each of these expectations with a Monte Carlo sample. So we're gonna call our Q hat ML, so our multi-level estimator, to be the sum of Y naught hat, so this is the Monte Carlo estimate of this expectation, plus the sum of the Monte Carlo estimates of all these expectations. And we'd like to note that each Y sub L hat is gonna be the difference between these correction terms evaluated using the same input data. So the J's are supposed to denote that they come from the same place, the same input data, but different grids. So why is multi-level Monte Carlo better than Monte Carlo? So we can look at the mean square error. First, our sampling error is gonna be fairly different. Instead of a single term, we now have a sum of the variances of our correction terms divided by the n, our sample number, n sub L. And the theory tells us that as L goes to infinity, our variance is gonna go to 0. So this means that the number of samples we're gonna need to keep the sampling error small is going to 0 as we get to finer and finer grids. This is really good because, as you all know, finer grids cost a lot more than the coarser grids, so we won't have to do as many solves on the fine grid, and the bulk of our processes will be on the coarse grid. So we can actually minimize the cost, constrained to our mean square error bound, and determine that the number of samples we'll need on each level is gonna go like the square root of the variance of our correction term YL divided by the cost. So the variance goes to 0, the cost is gonna increase as we go to finer meshes, so this number is gonna get really small as we go to finer meshes. So what we would like to do is we'd like to continue this process of variance reduction. And that will lead us into multi-level control variates. And this is the research we're working on, and it means to hopefully have to expend less cost to reach a solution. So what we're gonna do is we have this YL term, this correction term, and we're gonna construct a highly correlated ZL that's gonna be based on our YL data. It's gonna be a low rank approximation, and I'm gonna explain that in the next slide. And we're gonna construct a control variate based on these multi-level correction terms, Y and Z. So our WL is gonna be defined as YL minus this beta L term times ZL minus the expected value of ZL. And what we can do is we can choose beta to minimize the mean square error of W. And if we do the math and the algebra, it's a lot of fun, we'll find that the mean square error of W is gonna equal the mean square error of Y times 1 minus rho squared, where rho squared is given right here. It's a function of our YL and our ZL corrections. So our goal is to get rho squared as close to 1 as possible, and therefore this mean square error will become really small. So how do we form this Z? So we're going to use discrete empirical interpolation method, and we're going to define, well, we have our Y already defined. We're going to define the ZL as this QID, so it's this fine grid approximation minus our coarse grid quantity. And just to note, the coarse grid data for the Y and the Z are exactly the same. We're just trying to approximate this Q by this, the coarse grid interpolation. So how this is going to work is this process, DEIM, discrete empirical interpolation method, allows us to take a matrix of our coarse grid data. So these boldface Qs are the heat fluxes along the hot wall at the end of our simulation, and they're all vectors. So we'll have a collection of them in a matrix. And what it will do is it will pick capital R, so we pick capital R, it will pick capital R of these columns as a column space basis for the whole set. And it will also return these coefficients so that we can rewrite each of these columns as a linear combination of our representative basis. So then what we're going to do is we're going to use these input parameters that give us this representative basis, and we're going to run this, we're going to simulate these parameters on the fine grid. And we're going to get our coarse grid data, but only capital, we're going to get our fine grid data, but only capital R of these vectors. And then what we're going to do is we're going to use these coarse grid coefficients that we have from our first step, and we're going to use this fine grid data that we just got, our kind of our representative basis that we now have on our fine grid, and we're going to approximate all of our fine grid data using this linear combination of our coarse grid coefficients and our fine grid vectors, just capital R of them. And then what we're going to do is take the average, the mean of these to get this capital Q. So that gives us Z. I guess if we go back, so we have the Z term, and now we have this expected value of Z, which we don't know. So what we're going to have to do is we're going to have to estimate this value using Monte Carlo. And I should actually quickly point out that on our previous slide, sorry, let me go back one. This process is essentially free. The only extra cost is applying this DEIM process, but we're using all the same data we use for our multilevel Monte Carlo solver, or our YL corrections. But estimating ZL is going to come at an additional cost. So using the Monte Carlo, we're going to estimate our expected value, and our algorithm is going to be pretty similar, except we're going to draw NL prime independent samples from our coarse grid data. We're going to use our DEIM process, as we did in the previous slide, to determine our representative basis on the coarse grid, and we'll get these corresponding coefficients. So we have a lot of costs right now on the coarse grid, but then what we're going to do is run only capital R fine grid samples. So we're not going to have as much of a cost on our fine grid, because we can now represent our fine grid data as a linear combination of those basis vectors on our fine grid. And then we're going to approximate our expected value using Monte Carlo. And what's nice about this process is if we run multilevel control variates several times, we only have to really do this process once. So while it brings about an extra cost, we only have to do it one time offline. So back to the mean square error reduction, since we are using samples, we're using Monte Carlo samples, we'll actually find, well, I should back up and redefine. So now we can define our W now as a Monte Carlo sample of the Y's plus Monte Carlo samples of these terms. And what we can do is find the optimal mean square error when we're doing the Monte Carlo process. And that's going to be similar to what we had before, except we're going to have this extra fraction term. So our mean square error of our multilevel control variate term is going to be the mean square error of our multilevel Monte Carlo term plus what I've called this mean square error ratio, which is 1 minus rho squared times this additional fraction. So our rho squared is going to be similar to what it was before, and we want that to be close to 1. And then our optimal beta is given by beta star L. And all of these can be calculated with our data set that we use to calculate YL and ZL. So in pictures, because who doesn't like a good picture? So again, kind of as an overview, we can break this into two parts. We have our multi-level Monte Carlo process where we have NL samples. We input them into our coarse grid solver and to our fine grid solver to get our heat flux quantities. And then from there, we can get our y hat, our z hat, and our beta. So our Monte Carlo estimates for all of those terms. Then we'll have an independent set of input data with where we have n prime L, and we're gonna run it on the coarse grid to get our coarse grid data. Then from there, we use this DEIM process to get capital R of our input data, or it dictates which capital R we'd like, and then we're gonna run that on our fine grid to approximate this Q capital ID, so our interpolative decomposition of our fine grid data. And then taking that difference, we can get our mu hat sub z, so our estimator. And then put those all together and we'll get our W. So that was to try and bring it all back. So next we're gonna talk about our results. So what we're using is we're using data on 3 levels. We have a 16 by 16, a 32 by 32, and a 64 by 64. So this is our level 0, our level 1, and our level 2 meshes. And we're gonna do 100 rounds of multilevel Monte Carlo, multilevel control variate to determine the mean square error reduction we get, the relative error we get based on an approximate solution we have through compressive sampling, and then we're gonna do some cost comparisons. And we're gonna run 2 tests. So our first test is when we run multilevel control variates on all levels, levels 1 and 2. So our coarsest grid is just gonna be a Monte Carlo sample. Our second test is when we only apply it on our finest grid. So on level 2. So for test 1, what we're gonna find is that maybe I'll back up a sec. So all the red lines are our multilevel control variate data, and all the blue lines are multilevel Monte Carlo. So the plot on the left gives us our mean square error for each level. So we see that as we get to the finer levels, the mean square error of our W right here is gonna be smaller than the mean square error of our YL. This is good, this is what we want. This is why we're doing this. And then this plot on the right is the number of samples we're gonna need in each level. And because we get variance reduction as well, we're gonna find on every level we need fewer samples for our multilevel control variate process. And so now we're gonna look at the convergence of the relative error. And the bold lines, the solid lines, are our mean relative errors that we get after running 100 simulations. And then our dashed lines are gonna be plus and minus the standard deviation. And what we're gonna see is we have fairly similar relative error for this process. And what we're gonna do is we're gonna define one work unit as the cost to run a single simulation on the finest grid. And we're gonna find that multilevel control variates requires about 56% of the computational costs as multilevel Monte Carlo does to attain a similar accuracy. And this table on the right just has our work units. So 230 versus 404. So for test 2, we're only applying multilevel control variates to the finest grid. So we're only gonna see an improvement in the mean square error on level 2. And even though we're only applying it on the second level, we're gonna find that at each level we actually do have a reduction in the number of samples that we do need. Although we're gonna find that we have the greatest reduction on level 2. So again, we're gonna let one work unit be the cost to do one fine grid simulation. And what we find is by applying it only on the finest grid that we get an improvement in the relative error. And even with this improvement, we're not using as much computational cost. We're using about 80% of the computational cost of multilevel Monte Carlo. So 315 work units versus 394. So we're pretty happy with this. And so this is the end of my results. And then I guess to conclude, so on this specific problem, we're finding that we get improvement using multilevel control variates over multilevel Monte Carlo. Our future work would include using a formulation with particles, so this is that is our long-term project, as well as demonstrate the method on higher dimensional stochastic input methods and different problems, and also formalize the analysis and kind of develop the theory a bit more. And with that, that's all, so thank you.